In this section, we will look at the different types of error that can be made in a hypothesis test and consider these in the context of a Poisson distribution. After you have carried out a hypothesis test, you will either accept or reject the null hypothesis. In real life, this leads us to 4 possible outcomes. Either, in real life, the null hypothesis was actually correct, or the null hypothesis was actually incorrect. And in your test, you will either have rejected the null hypothesis, or you will have accepted the null hypothesis. So consider which of these situations have involved the test being correct in its acceptation or rejection. So this scenario involves the test being correct, as the null hypothesis was incorrect and the test rejected it. And in this situation, we have the null hypothesis was actually correct, and in the test it was accepted. The other 2 situations are errors in the test. So in the situation where the null hypothesis was actually correct, but it was rejected by the test, we would call this a type 1 error. In the situation where the null hypothesis was actually incorrect, but the test accepted it, we would call this a type 2 error. So in a type 1 error, the null hypothesis is rejected, but in reality it is actually true. An example of this was when we looked at the number of errors in a textbook. The author claimed that the chance of a mistake was 1 mistake in every 4 pages, and we rejected this null hypothesis based on an observation of 6 mistakes in 10 pages. If it had actually been true that the average number of mistakes was 1 mistake in 4 pages, we would have made a type 1 error in rejecting the null hypothesis. In a type 2 error, the null hypothesis is accepted, even though in reality it is false. So in the example we looked at with the 3-star restaurant upgraded to a 4-star restaurant, we accepted the null hypothesis. In other words, we rejected the idea that the star rating had changed the number of customers coming to the restaurant. If it turned out it was actually true that the upgrade to 4 stars had changed the mean number of customers, we would have made a type 2 error. We're now going to consider the random variable x with a Poisson distribution with a rate of 4. We're going to complete the table to show the probability distribution. So for each value of x, we can calculate the probability. We can then plot these on a graph. Suppose this Poisson distribution is used for a hypothesis test with a null hypothesis that lambda is 4 and an alternative hypothesis that lambda is less than 4. We want to know what test statistic we would need to observe in order to reject the null hypothesis if the significance level was set at 10%. In other words, we are looking for a value a such that the probability that x is less than or equal to a is less than 0.1. So we're going to go along and add up the probabilities until we get to a value just below 0.1. We can see here that the probabilities of x being 0 and 1 together add to 0.091, which is just below 0.1. If we were to add on the probability of x being 2, this would then take us above 0.1. So because the probability x is less than or equal to 1 is 0.091, we can say that a test statistic of 1 or less would reject the null hypothesis because 0.091 is just below 0.1. All of the test statistics that would reject the null hypothesis lie in the critical region. So in this case, x is 0 and x is 1 are both in the critical region. The test statistic that is at the limit of the critical region on the boundary is called the critical value. So in this case, x equals 1 is the critical value. All of the other test statistics that would involve accepting the null hypothesis all lie in the acceptance region. So x is 2 and above lie in the acceptance region. The probability of making a type 1 error is the same as the total number of all of the probabilities in the critical region. So for this test, the probability of making a type 1 error is 9.1%. We're now going to consider type 1 and type 2 errors in the context of a binomial distribution. So here we're going to let x be modelled with a binomial distribution with n equals 12 and p is 0.45. So this is the table of values for the distribution, and this is the graph that we get by plotting those probabilities. Suppose that there is a hypothesis test where the null hypothesis is that p is 0.45 and the alternative hypothesis is that p is greater than 0.45. We want to know what test statistic would we reject the null hypothesis if we had set a significance level of 5%. So in this case, we are considering the value of a such that the probability x is greater than or equal to a is less than 0.05. So we're going to add the probabilities together, but going from the right hand side until we get to a value just below 0.05. So we can see here that adding the 4 values on the right, that they add up to 0.036, which is just below 0.05. If we were to add on the probability for x being 8, this would take us over the 0.05. So the critical region here is x is greater than or equal to 9. The critical value in this case is 9. So if a test statistic of 9 or above would reject the null hypothesis in this test. Using the cumulative function on calculators, we would see that probability that x is less than or equal to 8 is 0.9644. We could then use this to calculate the probability x is greater than or equal to 9, which would arrive at the answer 0.036. In this distribution, the probability of making a type 1 error is 3.6%. We're now going to consider a binomial distribution hypothesis test with a null hypothesis of p is 0.45 and an alternative hypothesis that p does not equal 0.45. So we can see that this would be a two-tailed test. If we wanted to know what test statistic we would observe to reject the null hypothesis at a significance level of 5%, we need to divide this by 2 and consider the 2.5% at each end of the distribution. So first of all, we would look at the lower end, add up the probabilities until we get to a number just below 0.025, which is 2.5%. And then we would look at the upper end of the distribution, and we will be looking again for probabilities that add to just below 2.5%. So on the lower end, we can see that x equals 0 and x equals 1. Together, the probabilities combine to 0.009. This is the smallest value for which we would stay below 2.5%. For the upper end, we can see that adding the 3 probabilities at the top end would add up to 0.008. Again, this is the largest region we can find that would give us a probability less than 2.5%, as if we included 9, this would then take us over. Therefore, we can see critical values are 1 and 10. So if we observed a test statistic of either 1 or less or 10 or more, then we would use this to reject the null hypothesis. This is because the combined total of the two probabilities, 0.009 and 0.008, is less than 0.05. In this example, the significance level is a lot lower than 5%. So if we were to reject the null hypothesis, it would actually only be a significance level of 1.7%. In this distribution, the probability of making a type 1 error is 1.7%. Now complete exercise 5b on page 108.